is Jennifer, and I'm a senior at UMass, and I study public health
actually,
and
if you can do the
environmental
PowerPoint
science.
first.
And I guess I'll just briefly introduce the project that we've been working on throughout the semester. So we have been working on a water quality monitoring device using open source and the Arduino. And following the overall theme of the other projects, we have been looking for ways to use materials that are easy to get access to, usually things that you could find in your home and things that are low cost. And our design, using these low cost materials, we're trying to make a design that is very durable to withstand like inclement weather conditions. So we were basing our design off of another person's water quality monitoring device that we found on Public Lab called the Riffle. And basically what this person was doing, they were using a plastic water bottle, and I don't think they're using the Arduino, they're using something else, and it wasn't open source. So we are trying to make a device that was open source.
So I think they were using a non-Arduino device that they had ordered, they had printed specially, but the Riffle has actually split into a couple of different versions. So there's one version that uses the Riffle called the Riffle Ito, and then there's the Riffle itself, which is using something else. But one of the problems that the Riffle has had, despite a lot of development, is that you put it in a stream and you get it collecting conductivity data, which is essentially a measure of how much stuff is in the water. It measures the number of ions that are present. When they submerge it for a number of days or weeks, they bring it up and it's full of water. You know, no matter how much effort they put into that, that seems to be the biggest issue. So, well, I guess I'll talk about the first device that we made to try and get around that was to try and make it a little bit overkill and go, instead of a plastic water bottle, go for a PVC pipe. So this was sort of inspired by some bioreactors that folks in my department, by the way, I'm in environmental engineering is my department, had done. So they had sort of advised us on how to make this. So maybe I can put it under the camera here. So the cap is actually has these two pieces of metal, these two metal bolts, and that's actually what's measuring the conductivity. This other hole was for a thermistor, which measures temperature, to come out of. So we had tried this. We submerged it underwater for 24 hours, and when we pulled it up, it had about a quarter cup of water in it. So so it's hard to get this watertight when you're having wires and monitoring equipment coming out of it.
And so that led us into thinking of a different design that would keep out the water from getting in. And
so this one was designed using this program, Google SketchUp. And the idea was to go back towards something that's low cost and that people would have in their house. So this fits on the cap of a Jif peanut butter jar. And it's actually a mount for the Arduino as well. And the version that we have 3D printed is just sort of a rough draft, so it's very low density. So we haven't attached the Arduino to that physically, but I can show a demonstration of how this actually works. So if we have some water, and we take our Arduino, and so now what I'm going to do is I'm going to load the code onto the Arduino. This has the capability to log via SD card, but for our purposes, so I can show how it's measuring it, I'm going to plug it in to the computer. And hopefully this will work. Okay, so this is what the Arduino code looks like. And so if I upload it to the device,
Do you need the light on, or is that? Can't
Turn
find
the light
it.
on and then zoom out a little bit.
How do you turn the light on?
Where's the light switch?
how do I zoom? Oh, zoom. Wide.
Where's the light on?
And
So did you turn the light on?
I didn't see the light. Oh, there it is.
Okay.
Great. Okay, so it should be uploaded. And so if we see what it's actually doing, move the serial monitor, we see that it's, let's see, there it goes. Great. So it's logging to the SD card, and every couple seconds, every I think 3 seconds we set it to, it's giving us a conductivity and a temperature. So temperature about 22 degrees Celsius, and the conductivity is right now really high because it was using the paper. Now it's going to be even higher. So if we, or the resistance rather is higher. So if we submerge it in water, we see it changes. So now the temperature is a little bit lower, and we got a specific conductance about 47 or so. And by the way, this isn't calibrated. We're sort of waiting for the next iteration of the 3D printed version.
So now I'm going to add some salt to the water so we can see how the conductivity rate changes.
Oh, kids, we have pollution in the water.
Yeah.
Road salt, this time of year. So let me just adjust this. What do we have before 47, did I say?
Yes.
So now it's gone up. So you see it's, sorry, shoot. I should, hang on.
What?
Can you hold this? I realize this is really small for all of you, so let me zoom in. Okay. So it's giving us a specific conductance now that's higher. And it's going to level out after a little bit. It takes a little bit for it to get up to the value. So that's our demonstration.
So we have one more coming up, Jake, but any questions for Mark and Jennifer?
Peanut butter jar waterproof?
So we actually did a test, and initially it was not, but with a pretty slight modification it was. So you can get a gasket to go inside of it, and we just used one from a mason jar because the lid is the same size as a mason jar, and so that seemed to make it perfectly watertight. It's still has to be tested in the field, so that would.
Yeah. So in the beginning of the semester, another one of our goals was to, after making the device, to implement it into local streams like the Tan Brook, because there's a lot of students and faculty at UMass doing research on that, and they thought it would be a good idea to use our device in collecting some data. But unfortunately, because of time, we weren't able to reach that point. But I believe Mark is going to continue working on this next semester. Unfortunately, I won't be here to work on it.
I'm sad about that.
Yeah, but that was the overall goal of this device, is to actually get it collecting some useful data.
What was like what would you say the biggest challenge that you faced or are facing in advancing this project?
I think it's still kind of a disparate community. And so, I mean, it took me most of this semester to be able to navigate the public lab website with all of the forums going on currently with water quality monitoring. So I think that's, one thing about open source and open science movements is they're really great for engaging people, but they tend to sort of be disparate, and it's great that something like Public Lab is able to bring it together, but despite that, you still have a lot of different forms going on, and it's sometimes hard to converge around one, or maybe it's just a matter of iterating further before you converge on one idea.
Yeah, I mean, and I guess the other major challenge that I think a lot of the other projects as well faced was getting our devices to be waterproof. That was a bit, yeah, we're still working on that now, but I think we've made some progress.
Did you consider trying to actually just coat all the electronics with something waterproof and not have to put it in a container?
So, actually, like coat the Arduino.
In other words, make it so it didn't have to be in a waterproof container.
That didn't occur to me.
And this is why we want to do these kinds of sessions.
Yeah, I think there's more that you have to protect it from than just water. In a stream, you've got gravel coming along the bottom. You've got sticks coming through. And
The other thing that we forgot to mention is that we're also trying to get this to stay in the stream for an extended period of time. So it's logging data for at least a few days, so we don't have to keep going back and forth to the site to get the data. And I think that would require some kind of hard container to keep it waterproof and protected from other things. Yeah. Yes.
There's this process of making electronics so that they can withstand really, really harsh really harsh conditions, and it's called potting. Anyway, you should look into it.
potting,
It's really,
and it's something that I could do to say in Arduino.
Yeah, oh, definitely.
Yeah, because there's a lot of people who do it, and Arduinos are cheap, and you could actually pot one.
So also,
epoxy and dry
we
it
don't
to
own these
torture it.
Arduinos, but
Yeah.
I presume it would be hard to reverse that once you do it.
Yes, no, it's a one-way
Okay.
process.
Yep.
How long does the battery last, or have you
We
checked to see?
haven't tried it
So
yet.
we haven't tried it. It runs on a battery, but that's obviously something we need to know before we can deploy this. Yeah,
Have
we
you
don't
thought
know.
about maybe putting the sensors at the end of a really long lead, like a
Yeah.
30-foot
Yeah.
wire?
Yeah,
and
we
then you
thought
have
about
the
that.
device safely in somebody's
But-
house.
By the
Just have
time we
sensors.
thought about that, we were so far along. We're like, what's the point?
Yeah.
Yeah.
Yeah, so a more global question of the number of teams. So a common theme here is, and we've done this project, and now we're going to be continuing it on as a independent study. And I'm curious as to the number of projects or people for whom that's, this particular population, for whom that's the case. Is there, continuing on?
I plan on continuing this. It might not be as a for credit
Right,
thing, but
but there's still, the project wants to have a life beyond.
Well, maybe I could speak to that a little bit. One of the goals currently through the Public Lab research notes is my hope is that we get courses like this at least once a year, possibly every semester, and where these guys have been trying to write notes on this, so what Steve often calls instructables, so that we have instructables and maybe some of these devices can be left with the maker community here, and then next generation of students can read what they've done, pick up where they've stopped. So that's kind of one of the visions I think are, and I'm going to bring up Paula too, Paula Reese in a minute. But our group, our community, we're hoping that we can kind of get that rolling. And maybe some of you middle schoolers can help us with this stuff.
I'm bringing it up because I think when we look at the pedagogy of maker spaces, which is sometimes at odds with the structure of our institutions, that's one of the biggest challenges is here we have these living projects that have a life beyond the semester.
Yeah.
And much of their value is in being able to continue engaging in that life of the project, and how do we enable that?
Yeah. And the other thing I want to say is the dialogue we've just been having, where we're getting new ideas, this is why we want to do these kinds of events, so we can continue to build momentum and get ideas from people who have got lots of great ideas. So let me bring up thank you guys very much.